Yes, so I think maybe you've seen that this like small j kind of determines how close we can get. I mean, how small the angular momentum needs to be in order for stuff to be disrupted. And I hope you've played with the stuff, and maybe you kind of like had like a similar trend, basically, that this essentially tells you that that's like the flux you have normalized to the isotropic flux if you have like a beta of 0, basically. But maybe you've noticed that as you increase the anisotropy parameter, then you are actually having a faster faster diffusion, and I think it takes shorter amount of time to become to basically lose more stars. So the rates can be enhanced if you have some anisotropy. I think that was one of the kind of like toy models for this thing, and and we also kind of had this. Now we can go to this kind of loss con business, and I think the idea is that eventually, at least in this case, the energy was constant, but eventually it will be changed after some time. And the way to think about that is basically, basically I think what we're doing is essentially we're saying that maybe you have like a star here, and you have like a flyby maybe. Maybe we have some impact parameter b, and you can calculate, it flies pretty fast, and maybe you can calculate the typical change of the velocity after this flyby. Let's pretend it's fast enough, and it's basically going to be like the typical force we have times typical time that we're passing close to it. And if the first is like it's just energy, it's just gravitational force, so it's just gm over b squared, or this time is like b over v. So roughly it is going to be basically gm over bv. So that's nice. So that's basically the kick in velocity or energy or whatever you want that we're getting after one encounter. And maybe we can try and like see, okay, how long we have to wait for these things to accumulate until we can change the orbit completely, that it will have no memory of its initial conditions. And it will require a lot of scattering until we can a lot of small scatterings, which essentially you can think of it as a random walk. And I think so. The idea is that basically, if you're gonna try to calculate the first moment after, maybe you're gonna have a scattering from here, then from here, then from here. Eventually, if you're gonna try the first moment, the drift, it will kind of average out. So that's not good enough. You need to go further to the second moment to see like what would be like the net standard deviation of these things. So I think the way to write this is something like that, delta v squared. Essentially, it should be the rate of encounters maybe times basically the typical kick we get of each encounter, something like that. I think V-nature main does it properly. I'm just Anyway, so we can try and do that. So at least for the rate, we need the number density of the stars that we have in this environment times some cross section. So yeah, maybe we have some b, maybe we have some b plus db, so we have some maybe thin annulus or whatever. So it's gonna be roughly something times b times db. So it's like a differential cross section in some sense. And we also need the velocity, because that's the typical dispersion velocity that things are flying around each other. We're neglecting all the order unity factors. There's some pi and square root of 3 and etc. we don't care about, because it's, we don't have. So it's going to be like an order of magnitude estimate. So that's the rate that we have. And I'm just going to plug in maybe this delta v here, which is essentially g squared m squared over b squared v squared, which is nice. And then, so we have this. This is, why am I doing this, you wonder? Instead of the joy of seeing your faces. But yeah, basically, I think one of the b's cancels out. So we're going to have a db over b factor here, which is interesting. Times, I think we will have, let's see. Oh, I think it's still okay. Yes, and yeah, and basically we're gonna have g squared times m squared n over v, right? I think that's roughly what we have. So why am I doing this? Basically, so that's like true for like a particular analysis of impact parameters. Just pretend that, you know, it could, as Sten told me earlier, you can start from relatively like small encounters, but still this will be like not too strong. You can go like all the way to the edge of the system. So you're gonna have maybe much further encounters, but they're going to be more frequent because of the enhanced cross section. So what I'm trying to say is that you essentially need to integrate this over the range of possible impact parameters, because it's like a long range problem where the force falls off only as a power law and not as an exponent. Yeah, so the force, I think intuitively, yeah, so you need to integrate over this thing to get the actual change of velocity which is contributed from all the other stars, and it's g square m squared n over v.
It doesn't convert. That's
We'll get to it. So I'm just gonna write logarithm of b max over b min. Yeah, and the thing is that, okay, we have to introduce some cutoff because we're physicists, so that's what we do whenever things don't converge, right? No, okay, yeah. So anyway, for the b max, you know, at some point we're gonna exceed the sphere of influence, so we're just gonna cut off over there. That we can't really do these things anymore because it's not gonna be Keplerian. For the b min, there has been a condition that, you know, you can maybe have a small angle of deflection, but you cannot really do something like that. That's a strong encounter, and that means that this thing is not small, so you can't really. It's a different beast. So I think our b min is going to have some cutoff of roughly gm over the velocity squared, which is basically if you're going to have a scattering at this impact parameter, it's going to have like a 90 degrees deflection angle, which is, yeah, it essentially changes the energy in one step and not many. So that's not allowed in our game. Yeah, so sometimes this thing is called, I'm just going to mention that logarithm of b max of b min is sometimes called Coulomb. Sorry about my handwriting. My mother is a doctor, so it comes in with inheritance. So that would make you laugh, okay? Good. Coulomb logarithm, okay? And basically, as Sten already mentioned, maybe you should teach this next year. It comes usually from plasma physics, but also you have this kind of like long-range interactions because it should attribute to the Coulomb force, which is like the same thing up to a minus sign, essentially. It's an oversimplification, yeah. And that it basically means that, you know, if you have like some system with many orders of magnitude, many octaves of different dynamical range, you know, each logarithmic spacing will contribute the same amount of scattering in some sense. I think that's what it means. And this is because the area which goes as r squared cancels out with the force which goes as 1 over r squared, 1 over r squared. So it's roughly the same. Yeah, and finally, I think we can just write down the relaxation time. Sorry about that. Yeah, basically the relaxation time should be kind of like this thing over delta v squared. It's basically, you know, how long it takes this quantity to change by the order of itself. Sorry about my handwriting. I haven't used the whiteboard for a while. Yeah, and it is roughly v squared. I think we can kind of like plug in everything there. So it's g squared m squared n Coulomb logarithm. Yeah, sometimes it's called like lambda, just for the logarithm, I guess. And you're going to have another power from the velocity, so it's going to be like v cubed. And I think like at least add the sphere of influence. Sorry, influence. Oh, come on. Influence. It is roughly 10 gigayears, give or take, at least for our galactic center, which means that it is very long, and this fall into the lost cone. Nothing, but my mother is a doctor. That's funny. Okay. All right. So we're gonna have this. Thanks. I think it was only a partial disruption. Yeah. So we have this relaxation time scale. It is relatively long, and yeah, as we said. Okay, so it's very long. If we're at the sphere of influence. So maybe it's faster if we go closer to the center. And the answer is not really, which is a bit disappointing. Because essentially it's going to scale as, if we have like a density power law of some k as a power law, it should scale as this exponent of -3/2 plus k. And it seems like eventually, if you take a system and if you let it run long enough, it will develop some cuspy structure, mainly that the distribution of the number density, at least, or the density, yes, you're going to have more things concentrated inside, and that usually will have a particular power law, which is it's called the Bacall-Wolf cusp from the 70s. It's like some analytical, kind of like some estimate how to solve the Fokker-Planck equation, kind of like semi-analytically in some way. And yeah, and I think people have been doing simulations of galactic nuclei, and they've done either both n-body, like direct integration of n-body codes, and also Fokker-Planck formalism, and they kind of usually they get good results. They're roughly consistent, which is good. And like, yeah, but I guess like one way to get this Fokker-Planck roughly argument, it's kind of like eventually it's like a heuristic argument. Eventually you want to have some steady state, and usually, so I think people have tried to initially say, okay, maybe we need to have like a constant mass flux. So it means that the number density, total number of stars times the rate should be constant, and we can play with the numbers. We're going to get some power, but then it's not really correct. It's not the right quantity because there's no direction and it can go in or out. What we really want is actually the flux of energy, which could be very different. So we're just going to plug in another energy here, and if you go to these papers, you will hopefully be convinced that it should be this power law, and it's been like also verified numerically. As you can see here, that you have this kind of like steepish cusp. But also, if you're coming back to the question, okay, how does T relax? How is it as a function of the separation from the black hole? Actually, it's quite shallow. It's like only r to the 1/4. So it means that it means that it won't change that much. So relaxation, at least in maybe it's faster in globular clusters a bit, maybe open clusters, but I think for galactic nuclei like our own, it's going to be it's going to be quite slow, which maybe it's unfortunate. So maybe we can't redo TDEs still, but you've seen that you can in the code. So there must be something else, and that thing is this really lost cone. And the idea is the following. So basically, initially, maybe the stars start with some energy distribution, but they also have different angular momenta or different eccentricities. And two stars that have the same energy could have very different angular momenta, right? So so like one star could be, I need to delete these things. One star could have like a very circular orbit, and the other one could be very eccentric and eventually could be disrupted. So for example, if that's the massive black hole, one star is circular, the other one is very elongated, right? So they both have, maybe I'll do it with a different color. So so the black one, it has a circular angular momentum, which is basically GMA, where A is the mass of the supermassive black hole, while the eccentric one, okay, I'll call it LC. Basically, it means it has GM1 minus E squared, which, because it's very eccentric, it's essentially 2 times GN our pericenter. And let's pretend that, it's a Tidal radius here. So it's going to be the Tidal radius. And and therefore it is very small compared to the circular one. and you can like find like the typical fraction of these, orbits that we can assume. Yeah, and I think now maybe we can pretend that, system is relaxed enough in angular momentum, or at least in velocity. Yeah, let's say that the stars they had enough scattering such that their eccentricity distribution is eventually thermalized in some sense. So at least if you have like thermal eccentricity distribution, it means that basically this thing evolved is like 2 times E. It's something like that, between 0 and 1, I think. And basically the fraction of orbits that have eccentricity above some threshold of some critical one is essentially this integral. It's a silly integral, but okay. It's essentially 1 minus EC squared, which is exactly basically yeah, it's exactly this thing. So really the fraction of stars that will be disrupted is actually the square of this angular momentum ratio, at least for this case. And you can maybe think of it like as like a geometric effect. You could have like a cone like over there, and you want to be inside this like very narrow cone of some angle, or basically this is going to be the square of the angle in this geometric interpretation. Okay, so why am I telling you this? Because yeah, eventually, you start in the distribution, you scatter, maybe something escapes, maybe something gets close and scattered, but eventually that's like a way to move things around in some sense. And actually, yeah, and while the scattering doing all the heavy lifting, but eventually we're going to have like 2 different regimes in some sense. Now we can kind of ask, okay, we have like a population of stars, they're being scattered, and there's some sink, which is a tidal radius in some sense. There's also like a hose that diffuses stars into different locations on the phase space. So we can ask, okay, what's faster? If the diffusion rate is very fast, basically it's like having like a bath. We have like an open hose, and it flows like a river, and this thing is full. So we don't really. So if you want to calculate the rate of the disruptions or how fast this goes, we don't really care about the diffusion rate here. We care only about the size of the drain we have. The size of the tidal radius. So that will be in the full regime where the diffusion is fast enough. That is called the full loss cone. And on the other hand, if the diffusion is very slow, if this is clogged or if it's there's not enough, maybe this is wide enough. We don't really care how wide this drain is, because the flux really depends how fast you can replenish your bathtub or whatever. And this is basically the empty loss cone. And yes, so I think actually this thing is like a Japanese kanji, so I just learned this quite recently, because that means a river or a gawa, and it really looks like a river. So I really like this this design. And yeah, and essentially that's roughly what we have, because the number of stars, at least in the full regime, as here, the number of stars is like their total number times that time is like small angle of very small angular momentum. And yeah, and the typical time scale, if you have a star on some orbit, it takes like a time, it should be like at most the orbital period of this orbit to reach the pericenter. If you don't change it, and you don't, then typically you're going to have like a typical rate that is proportional to the tidal radius, and that goes with some function, some stiff function of the radius. So that's going to be like the full regime. On the other hand, if we really care how fast we can bring some drops of stars or water or whatever into the below and disrupt them, really what we care about is the diffusion of angular momentum. And I think you've already seen, at least in the first tutorial, that it's pretty fast compared to the diffusion in energy. This is because the initial angular momentum is quite small here. So you really need so it will occur faster. So if your pinhole is very small, the diffusion will be faster. And as again, this number of stars is the same, but the typical time scale we need to think about is actually how to change, how long it takes to change a our angular momentum if it's already close to the loss cone. So basically, we're going to just divide by this momentum diffusion timescale and not of the period, because we don't have. It's not what matters, because we can do many more periods until we go, and eventually, I think it's wrong here. It shouldn't be this way. I think it should be like relaxation timescale. So that should be like the relaxation timescale, not the tidal radius. So that's a typo. I apologize. I'll fix it later. It's only logarithmic with RT because again of these Coulomb arguments. So we're gonna have like two regimes basically, and maybe it's a good time to go. To go back to some to the plot we've seen earlier. So we can have like two regimes in some sense, and usually what will happen is that if for most systems, it's going to be a bit heuristic again. So let's pretend that typically in almost every system, you're going to have maybe some radius. So there's no numbers, it's just like a sketch, right? That's going to be maybe a flux. So usually you're going to have like some rise here, and maybe you're going to have some fall here, something like that. So this is going to be like the full regime. This is full because here the diffusion is really fast, as we discussed, because there's like more stars, and here there aren't that many stars, so the diffusion is very small. So here's maybe going to be empty. And usually that's going to be like typical scalings. And we will have some like critical point, maybe RC, where these two things are comparable. And usually most of the disrupted stars or whatever, they will be coming from these regions, because here we have like the most flux. It's the most efficient around this area. So usually, at least for if we'll have like a population of disrupted stars, they're usually going to be from from roughly like where these things are comparable. So I think that's why some people say, oh, it's half full, half empty, or whatever. But it's mainly because most of the stars are coming from these kind of areas. And I think maybe you already see it here, basically, in these kind of plots, because I think the source of most of these, they're usually coming like from the outer areas, maybe a bit further, but not too much. They can just go and plunge. While if you're too close, you can't really do it. Eventually, you can't really scatter too much because you'll have some other effects, and also it will be much slower. And and I think the typical rates are estimated to be like roughly 10 to the minus 4-ish per year, at least for these cases. I think that's what I had to say about all this loss cone business. Yes.
Does the number of stars cancel in this model?
Sorry?
It just seems like you're getting a rate that is independent of the number of stars that are orbiting the central black hole. Is that somehow canceled because of the...
Nah, I think it's just like a number that at least that is adequate for the galactic center.
Take some number. In other words, that scaling is for like 1 billion stars or something.
I think usually we scale these things either with either with the sphere of influence or with the mass of the supermassive black hole. But it's usually going to be like a very small, very shallow undependence usually, unless you have like a crazy structure of the cluster itself, which could happen sometimes. But you have some like non-standard assumptions. I think I'm going to like briefly touch upon these things. Okay. So that's at least that we have for two-body processes. In addition, we also have some other forms of relaxation, and this is a bit tricky. Because
Sorry, was there exactly what it said in the empty loss cone will start to destroy?
Sorry?
The type of the previous slide? I think
Yes.
there might have been a typo.
Maybe.
I think if you're saying the full loss cone, they're all destroyed. Empty is when they very gradually migrate in, so they have time to be
I think you're right.
partially disrupted.
Yes. I think for the full, you have like the diffusion is very fast, so you can move in and out of the tidal radius. Yes.
Right, but full means you can go in one perturbation, you go from being nowhere close to the massive black hole to being very, very close and getting immediately disrupted, right? Whereas empty means you go little by little, and when you go little by little, it's more likely to be a partial disruption, for example.
Because you can't change the pericenter too much because your kicks are much smaller because your diffusion rate is very slow. Yeah, no, I think here I meant is that, I think once you hit the tidal radius, you can't go back fast enough. So I think in the full you can temporarily be on a radial orbit, but be scattered away from it, because you don't really care about the diffusion itself. But yeah, let's talk about this. I shouldn't have invited you for this session. No, I'm kidding. Yeah, okay. Right, so LostCon, it's fun and confusing at the same time. Yes, and also there are also other forms of relaxation, which are a bit annoying. And I think the idea is the following, right? You have like a spherical cluster, and you have like point masses. You have like a collection of delta functions. So you can do this kind of like analysis of the relaxation of some scatterings. That's fine, but also, and we've seen that it changes everything. It changes the energy and momentum and everything, and that's very, very, very slow. Also, you can maybe average over the orbits of the stars, which are fast enough. And instead of stars or points, you're gonna have some rings. And then these rings, we're gonna have like different orientations, and eventually they're gonna be torquing each other, and they may change their shape with some typical time scale, but they can still preserve the energy, but they can change their ellipticity or angular momentum in this sense. And the thing is that, you're going to have some, because it's like not a smooth potential, but it has some like, it's not like uniform. You're going to have some residual stochastic force left, which is usually the typical gravitational force times some residual from the from some Poisson noise or whatever. And you can kind of like define like a similar relaxation process, right? You're going to have some typical variable, which is the angular momentum. You're going to have some residual torque, so that's like a typical time scale. And you're going to divide over some coherence time scale, which basically means how long these ellipses stay in the same place before they move significantly, and then their force is going to be like a new one. So it basically tells you, okay, how long does this force can remain coherent in some sense. I hope it's clear enough. I know it's confusing, but we can talk about that a bit more. Yeah.
Is this the three body?
No, it's resonant relaxation. It's a collective effect still. Yeah, free body is similar. You just have only two rings, but they're hierarchical, and the inner ring is torqued on a secular time scale. Yeah, it's a bit different. I think here you fix the rings for a coherence time Tc. You let the residual torque do its thing. Then you're gonna mix it up again because you have some precession, for example, of the pericenter. And then you're gonna have like a new forms. Yeah, you're gonna have a new configuration. Yeah, in any case, so the advantage is that this typical time scale is a bit faster. It is only the period times the mass ratio, but you can't really change the energy. You're changing only the angular momentum, for example. You can still make it eccentric. It still may be a possible mechanism, so that's fine. The other thing is that, but again, if you're and I think the question arises that, okay, what is this coherence time scale? So basically, it measures how long it takes for an ellipse to basically do this motion, to precess, to kind of like change its argument of pericenter. And usually, if you have some mass, if you have some different mass, at each radius the mass is different, that will induce some precession, because if it's eccentric, you see different mass in and out, so it's not really Keplerian. You're going to have some precession because you're seeing different mass at each point of the orbit. So that's this mass precession thing, this Tc. It's this thing, but also if you're very close, you're going to have some relativistic effects, right? Essentially, the closer you are to the gravitational radius, the faster your upside precession will be. It's the same thing as the Mercury, because I think Mercury moves a bit like, I forgot how many degrees per century, 17 arc seconds, something like that. Doesn't matter, yeah. Yeah, maybe, but it's like from this Postonian terms. And yeah, eventually if you're close enough, but if you're close enough, you're going to have less mass precession because you're going to have less stars, but GR is stronger, so you're going to feel it much more. And essentially, you can kind of like compare these two things roughly, and usually, at least for our number, it's roughly like almost yeah, it's like a fraction of a parsec in this case, which really depends on the power law. We're going to see how it really depends soon. And yeah, that's like the resonance relaxation. It really depends which time scale you have. And finally, you can also do the very brutal thing and wait a bit longer. You wait for the precession to kind of like do the entire circle processing. You can average over this time scale too. So instead of rings, you're going to get some annuli. And these annuli are going to like torque each other again, and they're going to change the orientation of the planes, but they won't change the angular momentum. So they're going to change the direction, but not the magnitude of the angular momentum, and that's sometimes called the vector resonance relaxation, which is faster, but you don't really change too many things. And yeah, I think that's like a typical table that kind of like summarizes like what typical timescales we have and different timescales of coherence, different timescales, what's conserved. So I think for the vector case, we really conserve the energy angular momentum. We just change the orientation a bit. It can matter, for example, if we have some disks of stars in the galactic center, and we've seen that they have some non-spherical contribution from observations that you did had this weird disk of stars sometimes, then it kind of like puts some upper limits on how strong these relaxation processes can be while they change the orientation of the stars we have in that environment. Yeah, and I think usually typical plots that people show is usually like these kind of things. We're gonna have tutorials soon on this soon after I finish the slides. Yes, I think as we said, if you have some typical separation and typical time scale. So for the two-body relaxation, it's almost fixed. It's like a very shallow slope for the typical relaxation of to change the energy. And the vector one is very fast, but again, it changes only the orientation of different orbits, but not really the magnitude of the angular momentum. And finally, for the relaxation timescales, at least one is for the upper one is like if you have like only one solar mass objects, and the lower one is for 10. Like if you have a cluster of black holes, for example, which are heavier, then it will look like that. You're going to have some transition. So you might expect that maybe in these areas, you're going to have maybe faster relaxation mechanisms. And you're going to have some turnover here, mainly because you're going to be in the GR precession zone over here. So hopefully you can get that also plotted soon. But yeah, just to get that. And I think like these disks over here that live here in the central log second, they are really here. So you really see that it's actually aligns of where you have this relaxation processes. Because if we further away here, you can still like maintain like a disky structure for a few mega years, which is roughly the typical time scale of these stellar disks. But if you're going a bit inward, you don't really have that structure anymore. You're going to have like a cluster of young stars, which are called the S-stars. So it really seems to be, at least in this picture, it seems to be working not too bad, I guess, hopefully. Unless you will find a way to break it down also. Sure you will. Yeah, in any case, so maybe I can remind you. So now we know what this RR means. So once we try to include this relaxation process, again, it's a very fast process. So if we just turn off precession of general relativity, for example, everything is going to be moving very fast because this resonance relaxation is really fast. It changes angular momentum quite rapidly. Well, energy doesn't do anything. So basically everything moves and disrupts, and and all the galaxy explodes and we all die, right? But luckily we have GR, so not everything explodes. It's quite limited. We have both positive precession and some dissipation from gravitational waves. And luckily, if we start low enough, we can't really move too much, because eventually, if we move close enough, if we're going to have like a very strong pericenter, then we're going to have what's known as gravitational wave capture. Basically, at this closest approach, we're going to extract enough energy from the orbit such that it would be kind of like decoupled from the environment and kind of like behave as an isolated binary evolution of some extreme mass ratio in spirals, for example. So luckily we have that saves us from too many disruptions and kind of like have more mergers. And I think that's usually what eventually happens of these dynamics of these galactic nuclei. And you can also like see it in actual, that's like a nice sketch, but you can also do some like actual kind of like Fokker-Planckish Monte Carlo simulations where you start somewhere here and you like increase the diffusion time scale in units of the energy diffusion, and you really see like, you can, eventually things start to diffuse here. Maybe you're going to have some disruptions here and there and maybe here, but if you're going to this area, eventually you will be captured and then it will just dissipate energy via gravitational waves. And yeah, and I think eventually once you kind of like take all this into account, you found that I think if you add resonant relaxation to your models, you do have some small enhancement, at least for the lower mass black holes, but it's really mild, I think, both, at least for the plunges. So yeah, it may change a bit, but not too much because of this barrier over here. So it doesn't really affect that much, at least for this case. Yeah, and finally, maybe a word of on TDEs a bit. So eventually, when you do this kind of modeling of galactic nuclei and some surveys, you basically think, yeah, you motivate your structure from some photometry of some galaxies. I think it's like different types, and you see you kind of have like a correlation. You have like a kind of like a, if you're going to lower masses, you're going to have like a mild increase of the rates, which is usually, yes, I think the parallel is roughly either a quarter or maybe 0.4. It depends, which galaxy it is. But also, I think maybe Katie mentioned, and I think we had some discussion that maybe there are a bit more TDEs in disruptions in maybe post-starburst galaxies. Basically, this E plus A means that it's like an elliptical galaxy, which will be like old enough, but it has like a recent overdensity of overabundance of A stars, which are quite young. So it means it had some unusual epoch of star formation that kind of like we see some residuals of it. That's all I know about observations, I think, and how to classify galaxies. But anyway, so maybe there's some overabundance in these ones. Maybe there's too few normal ones, and different people have tried to kind of like do these things. So I think here's a paper of my former office mate that basically took the Fokker-Planck formalism, added some, in order to preserve the distribution function, you need to have some sink term. That basically means, how fast you lose stars with this loss formalism, and also like a source term, because you just form stars somewhere. And at least in this case, initially, so I think you form stars in the first gigayear, and then you don't. I think that was the idealized case here. Essentially, you start, so the rates are very fast, and then eventually it slowly decays to its like nominal rate. So I think maybe there's something to it that you really, if you have some starburst, you do expect to have some enhanced rate, but it will die out eventually. And yeah, and I think the last thing is that eventually, as we've briefly mentioned gravitational wave captures, I think that's usually determined by this line basically, roughly, because you can just compare the time scales of the gravitational wave capture and the two-body relaxation, and whenever the dissipation from gravitational waves is faster, we will eventually, we won't be disrupting, we're just going to like be we're going to be like slowly in spiraling and not plunging. Yeah, I think it's actually the end of my slides, and I'm actually on time. Of course, there's like many stuff to do, and many things I haven't actually discussed, like binaries or other things, such as like massive perturbers, maybe different masses, mass spectrum, multicast, like so many stuff, anisotropies in the anisotropic nuclei, binaries, triples, like there's like so many things that we have neglected, but you kind of have to present something, right? Yeah, so anyway, I think the punchline is that most TDs are actually coming from kind of like far away, which is initially it was counterintuitive when we did the vote. I hope now you got like a gist of, okay, why does it actually make sense, hopefully, and that there's like much more rich things to do here.